Alrighty, friends, Unit 2, Day 7. This continues our look at implicit differentiation. On today's show, we look at how to find a second derivative if we know how to find a first derivative. So we're looking again at implicitly defined graphs, how to find derivatives and second derivatives. This will be our last day taking a look at such a thing. And then we'll move on to related rates problems, which are the same but different. So, want to do a couple of quickies with us in our 15 minutes? I want to find y double prime if 2x cubed minus 3y squared is 7. Now, 2x cubed minus 3y squared equals 7. We could graph that thing. It's one of those things where we could solve for y. We'd get plus or minus square root of a whole bunch of stuff. Nobody really wants to do that. And so since the graph is implicitly defined, we can give it a go. Let's do what we did yesterday. We take the derivatives of both sides with respect to x using the chain rule. So the derivative of 2x cubed is 6x squared. The derivative of 3y squared is 6y times dy dx, because we know that y is a function of x, so the derivative of that with respect to x is its derivative with respect to y times dy dx. And then the derivative of 7 is self-explanatory, so I want to get dy dx by itself. Well, that means that 6x squared is 6y dy dx, and dy dx turns out to be x squared over y. No big deal, but we're looking for the second derivative. We're looking for the derivative of this. So how do we take the derivative of that? We do it with the quotient rule. So the second derivative is the bottom times the derivative of the top minus the top times the derivative of the bottom. Wait a second. What's the derivative of y? Oh, the derivative of y is the derivative of y with respect to x. That's what it is. For the rest, you won't be scared. It's all over the bottom square. This is calc, this is calc, this is calc. So now the question is, what is dy dx? Well, dy dx is what we found in green. So all I have to do is clean that up. I've got to clean that up. It shouldn't be too bad. We're just going to multiply everybody through by y. And if we multiply everybody through by y, that's 2xy squared minus x to the fourth over y cubed. And even though we could factor a greatest common factor out of the numerator, it's not necessary to do that. That is d squared y over dx squared. So when we're finding second derivatives, or for that matter, any higher order derivative on an implicitly defined graph, we just find derivatives one at a time the way we're used to. Quotient rule usually comes into play on second derivative because so often we find our first derivative by factoring and canceling. All right, one more. Find the second derivative at 1, 1 if x cubed plus xy plus y cubed is 3. This is not an equation where it would be easy to get y by itself. This is a truly implicitly defined relation, and so I want to go very, very carefully. I want to find the first derivative. I want to do it in the way we've done it in the past. To find the first derivative, we're going to take the derivatives of both sides of the equation with respect to x using the chain rule. So that's a 3x squared plus. Now xy gets differentiated using the product rule. So The product rule is so much fun. It's first times derivative second plus second times derivative first plus the derivative of y cubed, that's 3y squared again, times dy dx, because the derivative of y with respect to x is the derivative of y with respect to x. And of course the derivative of 3 is 0. So now I want to get all my dy dx terms to one side. I'll do that by kicking the 3x squared and the y to the other side. And then I will factor out a dy dx and divide. Divide by what? Divide by x plus 3y squared. I should note, I'll throw in a quick side note here. At 1, 1. dy dx is what we get when we substitute 1 for x and 1 for y into dy dx. That's negative 3 minus 1 over 1 plus 3. That's negative 1. We're going to need that. We're going to need that because we're looking for second derivative. And since we're looking for second derivative, we've got to take the derivative of that quotient. And the derivative of that quotient comes from the familiar quotient rule. It's bottom times derivative top. Remembering that the derivative of negative 3x squared is straightforward, the derivative of y is dy dx minus the top times the derivative of the bottom. The derivative of x is 1. The derivative of 3y squared is 6y dy dx. For the rest, you won't be scared. It's all over the bottom square. This is calc. This is calc. This is calc. And so all we have to do is evaluate that at 1, 1. So how do I evaluate that at 1, 1? Well, x is 1, y is 1, so that's 1 plus 3. In parentheses, we've got negative 6 minus dy dx, but dy dx is negative 1 minus negative 3 minus 1, right? And then 1 plus 6 times negative 1 over 1 plus 3 squared. And that turns out to be negative 40 over 16. So really the only piece of new learning coming up in this lesson is how to extend a differentiation process to find higher order derivatives. Really, that's all I want us to be able to do. Every implicit differentiation problem has the same feel. If you learn the feel, that's a win. Hopefully, in watching this video and the one before it, you can see how every time we take a derivative with respect to x on both sides, collect everybody with a dy dx, factor, and divide. If you know that, then you've got everything you need. All right, that's it. I'm done. We'll see you tomorrow.